Imagine walking into a massive library with millions of books, but there is no catalog and no order to the shelves. Searching for a specific title would mean checking every single spine, one by one. In computer science, we call this a full table scan. Databases without indexes work exactly like this. They have to look at every record in the table to find what you need. As your data grows from hundreds to millions of rows, the time it takes to find a single piece of information grows linearly. This is why your favorite apps don't lag when searching through billions of posts. They use a clever data structure called an index. Today, we are going deep into the mechanics of database indexing, exploring why they are essential and how they transform a slow crawl into a lightning-fast jump. To understand the why, we first have to understand the how. When a database stores data on a disk, it usually writes it in the order it arrives. This is known as a heap. Finding a record by a non-indexed column, like a username in a billion-row table, forces the database engine to start at the very first byte and read until it finds a match. This is I/O intensive. Disk access is the slowest part of any computer operation. If your disk can read 1 million rows per second, a query on a billion rows would take 1,000 seconds. That's nearly 17 minutes of waiting just for one search. Indexes solve this by creating a sorted map that allows the database to skip the vast majority of the data. So, what exactly is an index? Think of it as a separate, smaller table that contains only two things: the value you are searching for and a pointer to where that data lives on the disk. It's like the index at the back of a textbook. You don't flip through every page to find photosynthesis. You look at the P section in the back, find the page number, and jump straight there. In a database, this back of the book is usually structured as a B tree. This structure is highly optimized for systems that read and write large blocks of data. It ensures that no matter how much data you have, the number of steps to find any individual record remains incredibly small and predictable.
Let's visualize a B tree. At the top, we have the root node. It contains ranges of values. If you're looking for the ID 50, the root might say, values 1 to 100 go left, 101 to 200 go right. You follow the pointer to a branch node, which narrows it down even further. Finally, you reach a leaf node. The leaf node contains the actual index entry and the pointer to the full row. This hierarchy is what makes indexes so powerful. For a table with 1 million rows, a well-balanced B tree might only be 3 or 4 levels deep. This means instead of checking a million records, the database only performs 4 comparisons. It's the difference between walking across a continent and taking a supersonic jet.
However, indexes are not magic, and they come with a cost. Every time you add an index, you are essentially creating a new physical file on the disk. This consumes storage space. But more importantly, every time you perform an insert, update, or delete on your table, the database must also update every single associated index to keep them in sync. If you have 10 indexes on a single table, one write operation becomes 11 write operations. This is the classic trade-off. Indexes make reads lightning fast, but make writes slower. This is why experienced developers don't just index every column. They carefully choose the columns that are used most frequently in where clauses or join conditions.
There are different types of indexes for different needs. The most common is the B tree, which we discussed. But there are also hash indexes, which are incredibly fast for exact matches, but useless for range queries, like finding everyone born between 1990 and 2000. Then there are GIN and GIST indexes, used for complex data, like full-text search or geographic coordinates. Choosing the right index type depends entirely on your query patterns. For example, if you're building a mapping app, a standard B tree won't help you find all coffee shops within 2 miles. You'd need a spatial index. Understanding these tools allows you to architect systems that scale efficiently as your user base grows.
Another advanced concept is the covering index. Usually, an index points you to the table to get the rest of the data. But if your index contains all the columns requested in the query, the database doesn't even have to look at the main table. It can return the result directly from the index. This is called an index-only scan, and it's the gold standard for performance because it avoids the extra step of jumping from the index structure back to the raw data storage.
By carefully designing your indexes to include frequently accessed columns, you can reduce disk I/O to the absolute minimum, making your application feel instantaneous to the end user.
But wait, why not just sort the main table itself? That's called a clustered index. In many databases, like MySQL's InnoDB, the table is the index. The rows are physically stored on disk in the order of the primary key. This is why searching by primary key is always the fastest possible operation. However, you can only have one clustered index per table because you can only sort the physical data in one way at a time. All other indexes are secondary indexes, which store a copy of the indexed column and the primary key value to find the rest of the row. This architecture is why choosing a good primary key, like an auto-incrementing integer or a UUID, is one of the most important decisions in database design.
To wrap up, indexes are the silent workhorses of the modern web. They allow us to store trillions of data points while maintaining the ability to find anything in milliseconds. But remember the rules of thumb. Index columns used in where, join, and order by clauses. Avoid indexing columns with low cardinality, like a gender column with only 2 or 3 values, as the database might decide a full scan is faster anyway. And finally, always monitor your index usage. Unused indexes are just dead weight, slowing down your writes and eating up your storage. With these principles, you'll be well on your way to mastering database performance.
Thanks for watching this deep dive into database indexing. If you found this helpful, hit the like button and subscribe for more technical explainers. We've barely scratched the surface of database internals, so let us know in the comments what you want to see next. From execution plans to concurrency control, there's a world of engineering hidden behind every query. Until next time, keep optimizing.